Hello everyone, I am Lionel Parreaux, an assistant professor at HKUST, and today I will talk to you about the so-called ultimate conditional syntax. As you probably know, pattern matching is the standard conditional expression form in functional languages, and the if-then-else form is understood as a special case of this pattern matching syntax. So if you look at an if A then B else C expression, you can really understand it as a case expression, so a pattern matching expression, matching on some scrutiny A for the two Boolean constructors, true and false. And this is actually how compilers like the Glasgow Haskell compiler represent if-then-else internally. But while pattern matching is very powerful and a staple of functional programming, the standard syntax for it also has limitations. For example, it is limited in the way it can match values in parallel and interleave bindings and computations. Essentially, to make pattern matching syntax really useful, a few extensions are needed, such as view patterns, pattern guards, active patterns, etc., etc. In this talk, I propose a new approach to conditionals in functional programming, where we go the other way. We start from if-then-else and generalize it until it subsumes all the features of pattern matching and more. We facetiously call this the ultimate conditional syntax, and it is being implemented in MLscript, a new ML family programming language that is being developed here in HKUST. The first idea is to reuse the concept of multi-way if that exists in other languages like Haskell, whereby one can write complex conditional expressions by matching on different conditions without having to use Verbose else if syntax. The semantics of the multi-way if is to evaluate the first branch so that the left-hand side evaluates to true. We generalize this notion of multi-way if to nested multi-way ifs using the AND logical connective in order to group together several conditions that have the same prefix. The second idea is to implement what we call conditional pattern flowing. In this language, matching values against patterns is done solely through the is keyword, which takes an expression as the left-hand side. Here the expression is x, and the patterns on its right-hand side. Here the pattern is 0 or 1. We can also bind variables in these patterns, and here's an example where we bind the pattern variable v. And we can also nest patterns as expected in functional programming languages. Here we are matching the result of the call to the function foo with a sum pattern whose value is either left of some v or right of some v. Variables bound in patterns are available in what we call the logical continuation of the conditional expression. So while the conditional expression returns a Boolean, it also binds some variables that are available in the corresponding branch of an if-then-else, for example, or in the rest of an expression that is constituted of an AND logical connective. For example, in this case, we are testing whether x is of the shape sum of v, and where this v is greater than 0. In the case above, we were testing if x is sum of v, in which case we return v, otherwise we return 0. In the else branch, v is not available, because in this case we don't know that x really has the shape sum of v. Importantly, each conditional expression can bind different sets of variables which become available depending on the truth of the expression. And here's a contrived example to illustrate this principle. The following expression is well typed, perhaps surprisingly. We are testing whether a given value x is not of the shape right of v, and if a value y is not of the shape sum of v, in which case we return a default value. Otherwise, we return v. So how does that make sense? Well, if you think about what this is logically equivalent to, you can see that we can reorganize the if-then-else in this way, where it becomes apparent that in the then branch, the value v is always bound, because it is bound in both parts of this OR condition. In the particular case where x is the same as y, we can also write the previous if-then-else expression in this more compact form by using a pattern alternation, which is represented using this vertical bar. We will not go through the formal rules of pattern flowing in this presentation, but the basic idea is that the typing rules for conditionals output two contexts, one for the true value of the expression and one for the false value of the expression. And these contexts are threaded through the conditional expressions in the expected way. Now let us compare what we have seen so far with Haskell's pattern guards. In Haskell, one can pattern match values using the case expression as follows, and one can additionally add set expressions to patterns. So here we are matching a pattern lit of some value where the value is greater than 0, in which case we return true, otherwise we return false. What makes pattern guards interesting is that they can themselves perform pattern matching. So in this case, we extract some x name of a variable var, and we access a context for this particular name x, which returns an optional value. If the result is some value and the value is greater than 0, then we return some of value. Otherwise, we do something else, and here there may be many more cases, including other cases that handle the var constructor. So this is how we handle the first example in MLscript. You can see that the return expression is a Boolean value composed of this isTest and a test that the value extracted from the isTest is greater than 0. And here is how the second, more interesting case is handled in MLscript. We pattern match on the value of e using the is construct if e is a var of some name x, and if the context contains a binding to some value for this name x, and if the value is greater than 0, then we return some of value. And we may handle many other possible cases here as before. With this example, I hope to have convinced you that the UCS is at least as powerful as Haskell's pattern guards, but that it's also more natural to write and easier to read and understand. As a small convenience, we also allow binding some parts of patterns using the as keyword, so that we do not have to repeat the sum of value expression here. Here's another good example of what we have seen so far. We can define a function zipWidth that zips two lists in input, applying a function f on each of their pairs of elements, and returns none if the two lists have a mismatched length. To do this, we simply test whether xs is an unempty list with x as the head and xs prime as the tail. Similarly for ys, in which case we call zipWidth recursively using xs prime and ys prime. And if the recursive call returns some of a tail, then we create a new list with the new head f of x and y and the tail that is returned by the recursive call. Otherwise, we simply return none. Here note that the foo of arg syntax is just syntax sugar for function application, where of is right associative and lowest precedence, just like Haskell's $sign. There is still a problem, though. In practice, many conditions will have the same prefix expression. For example, when we are testing x for equality with different possible values, and when we are testing whether a given temporary value has any of the given shapes. To avoid this repetition, the UCS allows one to split conditional expressions in arbitrary places and only provide the part of the conditional expression that is different in each of these branches. Notice in particular that we no longer need a temporary variable for the expression that is being pattern matched, thanks to this conditional splitting. Note that indentation is not essential to this ultimate conditional syntax approach, and we could use any other delimiter syntax, such as curly braces and semicolons. Here are some additional examples of conditional splits. We can split a conditional expression at the level of operators themselves, and in particular, method calls count as operators, so we can write expressions of this kind. Here we are testing whether a list XS has a sum that is greater than 0, in which case we return A. Otherwise, if it is nil, in which case we return B. And finally, otherwise we return C. Putting everything together, here's yet another example where we test if the result of some function call foo of u and v and w is sum of x, and if x is some value of left, then we return left defined. If it is some value of right, we return right defined. Otherwise, we return undefined if the result of the function is none. Notice that here we have not specified any arguments for the left constructor. This is simply a shorthand for specifying an argument that is an underscore. As a small convenience, we also allow intermediate let bindings at any point of a given conditional expression. For example, in the case where some value is not none, then this branch will not be taken, and we will execute this let binding, which will print a message to the console. Then, if the value has the following shape, which is a sum wrapper over a tuple of sum of name and value, then we can shadow the name binding by using a let binding that capitalizes it, and continue the flow of the current conditional expression by performing further pattern matching on value. Finally, if some value is sum of none, and on the right-hand side, either right or left, then we return anonymous. Now let us briefly explain our approach to type checking and compiling the ultimate conditional syntax. The first step is to unnest all the patterns into a core representation of pattern matching, which pattern matches one level at a time. Then we desugar all the pattern matching tests into traditional case-of constructs, handling all matched operands individually in their order of appearance. For example, the following conditional expression, if x is A and y is B, then C is D, is desugared as follows, where you notice that we have to introduce some join points in order to avoid duplicating some sub-expressions in the desugared version. Finally, we make sure during this process that all the cases are covered, otherwise we raise an exhaustiveness error. For example, consider the following program, which matches a given scrutiny X with two tuples, one where both components are true and one where neither component is true. MLscript desugars this expression into the following nested pattern matches, where it becomes apparent that we are missing some cases. In particular, we are missing the case for true and false and true. Now, this presentation would not be complete without mentioning the specificities of MLscript's type system. MLscript supports first-class union, intersection, negation, and literal types with some restrictions, as we will see. So, for example, you can type the following expression as being from an argument of type 0 or 1 into type A or B, where 0, 1, A, and B are singleton literal types. This pattern matching is exhaustive because we can restrict the type of the argument to be between 0 and 1. Things become more interesting with default cases. In the following pattern matching expression, we accept either the value 0 or the value 1, or a value of an arbitrary type A, which is not 0 and not 1, and this uses negation types to express this fact. As a result, we return either the value A or the value B, or the value of that A parameter that we passed in input. The details of this type system are to appear in our UPSLA 2022 paper, MLstruct Principal Type Inference in a Boolean Algebra of Structural Types. The reason we mention this is because this type system makes the task of type checking and desugaring the UCS much more complicated. First of all, notice that in MLscript, the union type made of the two tuple types 0 and 0 or 1 and 1 is actually equivalent to the seemingly less precise tuple type where each component is itself a union type. So in MLscript, this pattern match is still inexhaustive. The difficulty appears when we consider what to do for pattern matches of this shape. Here we have a composition of nested pattern matching on several subpatterns at the same time, as well as default cases. Then the question is, what is the desugaring of this expression? And in particular, what happens when we remove the last line? And how does this inexhaustiveness of this pattern matching manifest? We are still in the process of working out all the details of this UCS syntax in MLscript, and the complete elaboration rules for this feature is outside the scope of this presentation. In conclusion, we saw that the ultimate conditional syntax was a natural way of generalizing if-then-else expressions, allowing nested multi-way if-then-elses, pattern variables to be bound and to flow through logical continuations, and conditionals to be split in several continuations to avoid repeating the prefixes of conditions. Altogether, we argue that the UCS is a more flexible, natural, and readable way of writing functional programs that perform pattern matching, but not through the traditional pattern matching syntax and its extensions. As future work, we also intend to support imperative control structures, such as while statements, using the UCS in order to bind and flow patterns as part of the expression, such as in this example program, which decomposes a mutable list binding as long as it is non-empty and its head is greater than 0. Thank you for listening to this presentation. I hope you enjoyed it and this gave you some further language design ideas. The ultimate conditional syntax and MLscript are actively being developed, and they are available on GitHub at the following address.